A functional gauges is another method for verifying hole positions. The gauge design and fabrication can be costly, but if you're saving significant time, if you're making a lot of parts and you're invested in that part, it may be worth it. I'm actually working with a local machine shop that's looking at buying a $75,000 um, CMM to 100% inspect some parts that they could just build a functional gauge for. So they could save that much money and the cycle time and the cost of someone that knows how to program that CMM if they made a functional gauge, had someone else inspect and the gauge itself, and for a couple $1,000s they could probably set that up for the lifetime of the product. Okay, the gauges can reduce inspection labor when inspecting many parts. Labor savings may offset the cost of a gauging design and gauge fabrication. And process control of the product fabrication process may minimize needed inspection. The advantages of position tolerance. So what we have here in the left is an example of the location of two different acceptable holes, okay? And the blue represents how a traditional X and Y plus or minus tolerance zone would restrict those holes, and it would have to fall within the square. By using position tolerance, it becomes radial and you actually gain more uh, degrees of freedom in your tolerance because it's calculated as a radius from the center of the hole instead of just in an XY axis. Okay, so clarity of the requirement, only one correct interpretation. It's permitted at maximum amount of tolerance acceptable to the design. And round zones increase the tolerance zone area by 57%. So if you were to use old school X and Y dimensions opposed to position, you're losing that 57% of the area that could be a correct usable part. And maximum material condition and least material condition allow for additional tolerance on top of that, which you wouldn't have in an X and Y position. And freedom and flexibility to meet any design application, and specify necessary tolerance and applicable on any product geometry and applicable regardless of fabrication process. Clarity of position tolerances. So it's well defined in ASME Y14.5 2018. Tolerance zones located relative to reference datum planes, or datums, I'm sorry. Basic dimensions define feature true positions or theoretically perfect. And the freedom and flexibility to meet required level of control and range of design applications. And it's recognized in many industries, companies, and countries. Okay, ambiguity of coordinate location tolerances. So this would be the traditional way of measuring things without geometric tolerances. So not completely defined by any standard, unclear requirements force assumptions, possible tolerance accumulation subject to multiple interpretations, and incorrectly produced parts lead to disagreements that cause production delays and lost profits. The plus side, it's easier for people to understand. Okay, additional tolerance or bonus tolerance. Round tolerance zones are increased by the area by 57%. They further increase to obtain additional tolerance from MMC or LMC modifier. Increases acceptable amount of location variation. It increases producibility and reduces cost. And advantages only achieved by using position tolerances. Okay, counter bored holes. The position tolerance specifications apply to ensure the assembly of screw or bolt into a counterbore hole. 3 methods to achieve the result. The counterbore diameter calculations completed with the same formulas for calculating a clearance hole diameter. Okay, counterbore holes, 1 position tolerance, so it applies to the entire hole feature. Single position tolerance feature control frame next to hole and counterbore callout indicate the same position tolerance applies to the entire feature. Features act independently and may vary in opposite directions in the zone, but they're allowed to vary, but the tolerance still applies. Same values. And the virtual condition boundaries for the hole and counterbore if MMC modifiers included, because a lot of times these are made by 2 different tools, so you may have to calculate a different modifier for the counterbore than the through hole. Okay, counterbore holes in separate position tolerances. Separate position tolerances for a hole and counterbore. They would have to call different diameter tolerance zones desired for the 2 features. So if you do need to call them out separately, you can, but they need 2 separate frames. So just to review, in the previous example, you had 1 tolerance frame, and because there was only 1, it applies to both features. In this example, they're giving you additional tolerance for the counterbore. So the counterbore can be made at a looser tolerance than the through hole. And features act independently and may travel to opposite sides of respective zones. And the virtual condition boundary for the hole and counterbore if MMC modifiers included. Okay, counterbore is related to holes individually. Each counterbore reference is to each hole. So if it says 4 times, noted as applied individually. So you have to put the word individually there if you want them each individually measured and each individually compared. The datum feature symbol applied to 1 hole in the pattern with a note 4 times individually. The feature control frame applied to 1 counterbore with a note 4 times individually. I have never ever seen this in practice. So if you want to drive up your inspection costs, go for it. Especially with CNC machines, they're going to cut the positions relative to each other. They're all going to be off about the same because it has to do with setting up the part. When you're making something manually, you could get the position off different for each hole, but on a CNC machine, it's going to be off. The position is going to be off the same on every same type feature that's called out. They're cut with the same tool, cut in the same fixture, cut to the same origin. If they make a mistake on setting up origin or the drill's walking because of the feeds and speeds, generally they're all going to behave the same. So I think it's way overkill to put individually. And each hole serves as a datum feature for its respective counterbore. Consider tolerance accumulations on holes and counterbores. It'd be just easier to loosen up the tolerance on the counterbore, and then it just takes care of it. Application to threads. Now, I've mediated lots of disputes on this, and there's company policies that may vary from the standard, but position tolerance is applicable to the location of the pitch cylinder axis. So what is that? The pitch cylinder is the average between the major and minor diameter of the thread. So it's halfway. It's called the pitch diameter when you're measuring it. It's a theoretical place. You got to measure the top and bottom of the thread in order to derive at that number. There's no physical cylinder really to check. It's an average between the top and bottom of the thread. The axis method of verification must be used, and notation minor diameter or major diameters if necessary to apply position tolerance. So, from a practical standpoint, if you're going to call position, to a thread, and you're going to use maximum or least material condition modifier, then you should call out whether you're measuring that to the major or the minor diameter. Otherwise, you drive your inspection cost up because they have to measure the difference between the major and minor and figure out where this theoretical cylinder axis. Now, I have been at 2 companies that by policy do not apply maximum material condition to threaded features. It made it regardless of feature size, probably because they don't want their people spending all of this time trying to calculate threads, which are unreliable on checking. So it is what it is. The example in the book shows all these examples with maximum material condition for threaded holes. I don't know how much it's used in the application. It can be done. It's expensive. Applies it regardless of feature size or MMC, depending on preference and certain factors. On another note, on clearance holes, you almost always put maximum material condition. Okay, projected tolerance zone. Okay, it lies outside the tolerance feature. So, like in this example, you got 2 holes and a pin. The pin projects outside of the part. So if you're interested in controlling it after it is assembled, you could have a projected tolerance zone on the hole feature. So when they're made, they've got to be accurate, extending outside theoretically the hole, so that when your pin presses in, it's going to be located in its assembly state in the correct area. So the projected tolerance zone symbol and projection distance is specified in the position tolerance feature control frame. It establishes no requirement for feature location within the part. And verification through axis method. Okay, projection tolerance zones and models. Okay, it's specified by terminating the annotation leader on the hole at the surface tolerance zone projection. So it's important that the side you want the projection to go in is the side that you've referenced in the plane in the model itself. Otherwise, you're telling it to project in the opposite direction. So it is important what surface you associate it with the hole for a projected tolerance. Ensure the leader is attached to the correct surface for the through hole. Projection tolerance zones with orthographic views, okay, specified on a blind hole through projected tolerance zone symbol and projection distance, and indicate the direction of the tolerance zone extends if the hole passes through a part. And a heavy chain line is drawn adjacent to the controlled axis, extending in the direction of the projection. So in my experience, I've rarely ever seen this applied, but I think it might be industry specific. If you have assemblies that are going to have, say, long shafts that come out of a hole and you need to control that at the assembly level, this is where you would project this. You have the letter P, and in the orthographic view, you're going to have this heavy, they call it a chain line, but it's probably a heavy phantom line or center line that shows the projected distance. And in this case, it has to be held within position a ½ inch above the part. So that's actually kind of difficult. Okay, bidirectional position tolerances. Okay, so this is using position on something like a slot, something that's not round. Permits more position tolerance in one direction than the other, and rectangular tolerance zone, and specified relative to the datum feature reference and well-defined true position. And may be specified at MMC or LMC modifier. And a virtual condition is created when the tolerances are specified at maximum material condition. So if we look at the example on the left here, we have a slot, and they're allowing 60 thousandths of position on the half-inch dimension, but they want to hold the slot in the other axis more accurately at 14 thousandths of position. So if you think about how a slot would function, it's designed to allow a part assembly to be positioned and adjusted in one axis. So in the axis that it's adjustable, which is the axis of the long end of the slot, they're allowing a lot more position tolerance because it doesn't matter, because that's what the slot's for and it's also easier to hold the tolerance on the width. They don't want that much play in the part on the opposite direction with the fastener. And so your end mill and your machinist, you're going to need to be able to control pretty much cutter flex is what you're trying to control here in the direction of the 188 thousandths slot width. Okay, non-cylindrical features of size. Position tolerance, specified location requirements for slots, tabs, and rails. The tolerance specification adjacent to feature size, dimension, or attached to the dimension line itself. Do not place the feature control frame on an extension line. Okay, position tolerance at MMC for a slot. You can use a surface method or axis method. Surface method has precedence if differing outcomes. So if you have parts that have a lot of variation, you generally want to use a surface method. So that would be calculating the virtual condition and having a functional gauge. Your tolerance zone is on a center plane with the axis method. Okay, so two different ways to calculate the same tolerance. Okay, bound features. Now, I believe this is getting pretty complicated, and you have to have a sophisticated inspection department to do parts this way. It is a trend to go this way with companies that are model-based definition. I don't know if I agree with it because the rest of the world is not prepared to do this, and so the companies I've worked for will go back and have an engineer reinterpret this and make drawings for their shop. So, and it also is, to be honest with you, a little bit lazy on the engineer side. If you just point at something and say everything in it has to be held to a tolerance, and it's not really needing to follow a specific shape, you're driving up the cost of your part for no reason. Okay, so the position tolerance may be applied to a boundary feature with a profile tolerance. So a bound feature would be profile tolerance. So in the example on the left, this entire pocket or window feature they have here has to be held within a profile tolerance of 20 thousandths to datum A, which is the back of the part. Typically, profile tolerances will only have one datum, and all that's saying is the wall of that profile needs to be 90 degrees to datum A. Other than that, it can vary in a zone, shown on the bottom, of 20 thousandths. Now you have a position tolerance of that same profile, and if it's a complex shape, it's another boundary within there. But yeah, how do you got to go back and measure this in multiple points to calculate this. So wouldn't you want multiple dimensions associated with those to make it easier on the folks doing the inspection? I don't know. This kind of forces it to go into a CMM. Is the part really that critical that that envelope needs to be held at a profile tolerance like that? Typically, the better application for this is when you have an absolute critical contoured shape, like an aircraft cross section, and it's not geometric driven; it's driven by a data table, airfoils, that kind of thing, in my opinion. Profile tolerance establishes the maximum material condition boundary. The position tolerance defines allowable location variation within that boundary. And notation boundary beneath the position tolerance feature control frame is allowable but not recommended. Okay, we're getting towards the end here. Thank you for sticking with me. This is a longer lecture, and this is just the first one on position. And this one frame is used ubiquitously. We have position tolerance with no datum feature reference. Okay, it's allowed only where the tolerance features identified as the datum feature and referenced as the primary datum feature in other feature control frames. So they're not putting a datum there because it itself is the datum A. And you notice it's a very tight tolerance, so that diameter is absolutely critical to the function of this part. And so it drives all the other datums. In summary, in this lesson, we built a foundational understanding of how position tolerances are applied to ensure precision and functionality in manufactured parts. You learned how to correctly complete feature control frames using the diameter symbol MMC, LMC, and RFS, and proper datum references. We explored how to visualize and sketch tolerance zones, calculate tolerances under various fastener conditions, and determine bonus tolerance when applicable. Through practical examples and hands-on calculations, you gain insights on how these tolerances work in real-world scenarios and why they offer significant advantages over traditional coordinate-based tolerancing methods. In conclusion, by the end of this lesson, you were able to complete feature control frames for position tolerances properly using the diameter, material condition modifiers, and datum feature references. And you were able to sketch the proper location and shape for position tolerances, describe the effect of MMC, LMC, and RFS applicability on a position tolerance, and provide examples that prove the validity of maximum material condition concept as it applies to position tolerances. You're also able to calculate position tolerances for simple fixed and floating fastener conditions, calculate the allowable additional tolerance or bonus tolerance for a produced part on which a position tolerance is at maximum material condition, use the calculation techniques to verify whether produced hole locations meet specifications on the drawing tolerances, and cite the advantages of position tolerances when compared to coordinate hole location tolerances. Thanks again for sticking with me in this lecture, and we will see you on the next one.